So in this session we will start learning with the Spark SQL. So as I said earlier, Spark is a platform for different kinds of data processing. So one of the kind of data processing that we'll be doing is the Spark SQL. Now Spark SQL is a library in the Spark framework. And the main use of this library is, or we can say Spark SQL is all about processing structured data. So that's the main goal of processing using the Spark SQL to process the structured data here. Now, what are structured data? What are unstructured data? And there is a one more category like semi-structured data. Let's see a brief details on that. So we have structured data. So what are structured data in general? In general, structured data are nothing but the data which has the complete information about the data, or we can say the complete schema of the data. For example, RDBMS data is a structured data. RDBMS data like MySQL, Oracle, Postgres, all these contains the structured data, meaning there is a table name, the database name, the column names, column data types, the location of the file. All the details are available of the data. Mainly table name, column names, and the data type. You get the complete information of the data. That's what we call as a structured data. Some NoSQL data are also structured data. So we can think of Avro, Parquet. We haven't discussed these things, ORC, but these are also a category of structured data because there will be schema associated with them. Complete details of the schema will be there. In a similar fashion, we have semi-structured data. Now, what is semi-structured data? Where we don't have the complete schema available. There is a partial schema available of our data. For example, CSV data, XML data, JSON data. These are the examples of semi-structured data. Because if you see the CSV, if you take for example the sales.csv itself, there is a partial structure associated with the data, meaning your each line is a record. That is one structure. Each fields are separated by comma, so that is a structure. There is some structure associated with that, but you don't usually have the data type in the file. So there is no data type of the individual fields specified. So hence we call it as a semi-structured data. So there is a partial schema available saying this is a record. Each record is separated by comma, but there is no data type of individual fields. We don't know the data type of transaction ID. We don't know the data type of nowhere it is specified. So hence such things are called as semi-structured data. Similarly, if you see, JSON record will also have the same thing. It will be separated in the form of a key value pair. A colon will be there. If you see the JSON, sales.json, so there is a structure associated. This is one JSON record. Open flower bracket and close flower bracket gives the boundary of a record. Fields are separated by semicolon. Fields are separated by semicolon. Field name and value is separated by a colon. So these are all the structures of your data, but there is nowhere specified the data type of transaction ID, the data type of customer ID. So again, XML JSON is a semi-structured data. In a similar fashion, XML is also a semi-structured data because there is a structure associated and not the data type. So in a similar fashion, we have unstructured data. Now, what is unstructured data? Unstructured data are nothing but your audio samples, video recordings or videos, image, text. So these are all the unstructured data. I'm not sure about the mainframe files. Are you saying the database, mainframe database? Okay, okay. I'm not sure, Anand, because I haven't worked on those files. But the generic idea is this. There will be some audio here. Now, if I want to know which all words has been used in this audio conversation, there was some audio conversation happening. So, which all words are being used in this audio conversation, and how many times those words are being used? It's not a straightforward. You cannot just run a SQL query on your audio sample and get all the words and count the how many times it has happened. So first you have to recognize those words using some speech recognitions. So such data are actually unstructured data. Similarly, in the video, you want to check which video, whether something is being, which game is being played, which competition is being played. Such kind of uh, things. So some any theft is being happening. All those, if you want to detect, you cannot just write a SQL query on that. So obviously, some algorithms are required here. To understand these audio samples, to understand these video samples, some algorithms are used here. That's where uh, your artificial intelligence and or machine learning comes into picture. To handle such kind of a data, usually there will be algorithms, hence it belongs to artificial intelligence or machine learning. Now, as per Spark, as I said, that Spark SQL is all about processing structured data. So, but from the Spark's perspective, it treats these two as a structured data. It not just treats the normal structured data as a structured data like MySQL, Oracle, or Postgres. This it also treats normal semi-structured data also as structured data. So Spark SQL is all about processing these kinds of data. So to process these things, Spark SQL has certain components. The very first component is nothing but Datasource API. So Datasource API is nothing but a universal API to read or write any structured data. That's the Datasource API. It's the input output module of your Spark SQL library. It only deals with the reading of your data from the file system and writing the data to the file system. File system, DB, NoSQL, anywhere. So it's one single API. Just like we have our text file API to read the data, we have sequence file API, we have binary API. In Spark Core, those are all the APIs that is available. But in Spark SQL, we usually use the data source API. We will see the example. So it also has ability to discover schema. It has the ability to discover schema. Meaning if we use the data source API to read this JSON file, if we use data source API to read this JSON file, it will automatically discover that a transaction ID will be an integer, customer ID will be integer, item ID will be integer, and amount paid will be double. So it has that ability. That data source API has that ability. So that's the first thing, because always we want to read the data, so we use the data source API. The second one is nothing but the component is nothing but data frames. Data frames is nothing but high level representation of your data. Earlier we were representing our data as RDD. Now we will be representing our data as data frames. Here is a question. The question is whether data set and data source is same. No, they are not same. We'll see what is a data set. So data frames are nothing but high level representation of our data. It's just the way it is also just like your RDD. Whatever we talked about RDD, like RDD is a collection asset. RDD is a immutable collection. RDD, any operations on RDD are lazy. Most of the transformations on RDD is lazy. Actions on the RDD trigger the lazy expression. RDD is immutable. RDD can be cached. RDD is distributed. So all those things holds good for data frame is also the same thing. Data frame is also a collection. But only thing is, along with that, it also has a schema. Right, right. Internally, it is a RDD, we can say. Internally, we can think of data frames are also just like a RDD. I mean, it's you can think of in that way, but slightly all the things is different. You can imagine that data frames are just like RD, but internally lot of things are different. So it is as of now what you can keep in mind here is Data frames are nothing but RDD plus the schema. So which is nothing but RDD is nothing but collection of rows, collection of records or rows plus schema. So this is our data frame. It has the schema also. So it also looks like when we say rows plus schema, you can compare it with the table, because what is a table? Table is nothing but collection of rows plus schema. So just you can keep in mind that data frames are nothing but your table, which is a collection of rows plus schema you have. So that's the high level representation of your data you can think of. But internally it is all about your SQL engine implementation. If anybody wants to implement SQL, irrespective of whether it is a Spark SQL, Kafka SQL, or normal RDBMS SQL like MySQL or Oracle SQL or Windows SQL Server, anybody who wants to develop an SQL engine, SQL framework, so they will be using tree data structure everywhere. That's the standard way of developing any SQL. Tree data structures, and tree data structures are being used to create logical plans, analyzed plans, optimized plans, physical plans. So your tree data structure is used to represent all these plans. Your logical plan will be actually a tree. Your analyzed plan will be one more tree. So your optimized plan will be again a tree. Internally, the tree data structures will be used to implement an SQL framework. The same thing is done in data frames also. So since we can imagine it to be like a table, since we can imagine it could be a table, so internally when we say table, it is all related to SQL. So internally you will be seeing a lot of tree data structures with SQL logical plans, optimized plans, physical plans, all those stuff. So I hope Samir that was clear. Even though we can imagine internally it to be a RDD, but lot of other changes are there, because you just cannot use just a representation as RDD, but it will be a complete SQL engine. It's a complete. So we usually don't care about the SQL engine, because if you see most of the SQL experts, they will write SQL query without worrying how the tree data structure is implemented. So we don't have to worry about the tree data structure how it is implemented. So we have to give the SQL queries. Now, and where do we get the schema from? As I said, data frames is a high level representation of your data. So where do we get the schema? The schema is got from the Datasource API. So Datasource API, since it has the ability to discover the schema, so that we get the schema from there. It has the ability to or discover the schema, ability to accept the schema. I mean, we can explicitly specify the schema. As a developer, we can give a schema as the input, and the data source API will accept that schema. In that case, it did not discover the scheme. So these two are the components. Now since our data is in the form of a table, I mean, like we can imagine now data frames is like a table. Now once we have the table, obviously we can give SQL queries on our data frames. So since we can give SQL queries on our data frames, so obviously our Spark SQL library should have SQL parser and optimizer. SQL parser and optimizer. So optimizer here in Spark SQL is called as catalyst. So this catalyst is the one which will which will optimize your analyzed plan. So this is done by the catalyst. You have your logical plan, then the logical plan will be analyzed. After analyzing, we get the analyzed plan. Then it will be converted into an optimized plan by the catalyst. Just like we do it in the MySQL or any other SQL engine. One more component we have is Hive Thrift service or Hive Thrift service. After that, we have our Tungsten. These are the components of your Spark SQL library you can think of. Now, what is this Hive Thrift server and what is this Tungsten? So earlier days we know that earlier days we have BI tools. BI tools like Tableau, we have ClickView, lot of stuffs are there. BI intelligence tools. So they used to connect to MySQL. Here we used to give the queries. So the queries would be sent to the MySQL server. MySQL server, it would do all kinds of processing and give back the results. So this again, as and as data started growing, the query time increased. We know that these are all the earlier case before Hadoop we had. So later what happened, since it used to take a lot of time to to give the results, so it was removed. Instead of that, we got our Hive server. Hive server is just an interface on top of MapReduce. Earlier it was in this fashion. And our data will be existing in the file system. In the file system, we had the data. Instead of saving the data in MySQL, we exported the data from the MySQL to, I mean, we still have the data in MySQL. So we exported and saved the data to MySQL. Now the BI tools will be connecting to the Hive server and the queries will be given. and the queries will be given here. So the Hive server is again just like a SQL engine. It is just like an SQL engine which will go through, parse your query, prepare the logical plan, prepare the optimized plan, prepare the physical plan. Your physical plan will be nothing but a MapReduce application which will read the data from your HDFS, start processing the data, and it will return the result, but in a distributed fashion. Your MySQL was not in a distributed fashion, so your query results will be much faster in it. Comparatively, it will be much faster. So that's where, so so here what happens here is they have implemented Hive Thrift service, or thrift service. Hence they call it as a Hive Thrift service. So again, it is a serialization. Thrift framework is a serialization framework. The serialization helps you to connect the data from, so sorry, to connect from any BI tool. The thrift service main use is you will have a BI tool which is implemented in Java. Any language based BI tool can be used. You can have a one more BI tool which is implemented in Python. You can have a BI tool which is implemented using Ruby on Rails. Different web framework. So everybody can connect to this Hive server because Thrift server makes that as an abstraction. Thrift service is an abstraction which can handle cross-language platform. Any language-based BI tool can connect to your Hive server without any worry because the Thrift service will take care of the serialization. With any language it is being written, the objects will be serialized as could be understand. So that's where the thrift service comes into picture. Now Spark is also SQL. We know that Spark, we just discussed that this is our Spark SQL. This is our Spark SQL libraries. We can make this Spark SQL library as a SQL engine. Just like Hive server is there, we can make that. So instead of using Hive server, we can directly use Spark SQL. We can directly use the Spark SQL. If we use the Spark SQL, but the BI tool should be able to connect to our Spark SQL engine. When we make our Spark SQL library as expose the Spark SQL library as a Spark SQL engine, so the BI tools should be able to connect to that engine and start giving the queries. So you don't want the BI tools to make lot of changes to their software. Nobody wants their software to be modified as and as you connect to new SQL engines. So what Spark they have done is they have taken the same code of the thrift service and they have integrated here. Hence we call it as a Hive thrift service because the code is taken from the Hive thrift service. So which makes the BI tools, any BI tools to connect to the Spark SQL. Not much changes is required on the BI side. Not much changes is required on the BI side. So they can seamlessly connect to your Spark SQL because the thrift service gives you the abstraction. So any queries given here will be sent to the Spark SQL. It will prepare logical plan It will prepare logical plan, analyzed plan. Sorry, what I'm writing. Logical plan, analyzed plan, physical plan. So your physical plan will be something like RDD code. Your physical plan will be here, RDD code, and that RDD application code will be run to read the data from the HDFS file systems and process the data, get the results and send it back to the BI tools. So this is where that thrift service comes into picture. So to put a bigger to give a bigger picture of this, let's say we have in this fashion. So we have a team called data engineering. There is a data engineering team and there is data analyst team. So the data engineering team usually does the ETL process of your data. Let's say you have some server. You have some server where your client is putting the data. The client sends and they always send the data to this server, which is exposed to the client. So this is our HDFS. This is our HDFS. From the server, the data will be stored here. This is our raw data, we'll say. This is our raw data. Now this raw data will be read. It could be Spark. Our Spark application can read this data, do some ETL processing on that, kind of a error handling, joining with some other data. So anything it can do. Join with other data, enrich the data with something, remove the error records, remove unnecessary records, select only the required fields, select only the required columns, and save it again back. Let's say which is a processed data. This is our processed data. Again, we have processed data. So the Spark will read this data, process it again to some optimization may be required, or the way the data analyst want to give the query, you make your data suitable to that query. So data analysts are the ones they will be giving the queries. So they want the data in certain format. So your Spark SQL will or Spark can be used for that purpose. I mean to say you make your data suitable for such queries and finally save it. Let's say we call it as a warehouse there. So Spark earlier all these things were done with MapReduce, Hive, Pig. Now you can solve these things with Spark or in combination with Hive and Spark. You can achieve the whole thing with combination with Hive and Spark, combination with Pig and Spark, combination with Hive, Pig and Spark, or you can only use the Spark framework here for doing all these ETL processes. So on hourly basis, your data is dumped to the raw directory. From that, your Spark application can process, or Hive can read the data, do some ETL, or Pig can read the data and do some ETL and save it to some product process directory. Again, some more processing is required. So again you can have do it with MapReduce or or Hive or Fig. These frameworks could be used here. Now once you have your data in the required format, so the file format could also be optimized. Here, whenever the data is stored as a raw data, it will be in the text format. It could be a CSV file, it could be a JSON file, or it could be an XML file. So once you process, you may save it as a ORC or Parquet file. Here also you can be stored as a ORC or Parquet file, which is an optimized file format. Now the things that is exposed to the data analyst is, so they may be using some BI tool. BI tool 1, some BI tool. BI tool 1, BI tool 2, and we have the Hive server here. So you give the query here, the queries are given here, and this Hive server will take that query, parse that query, prepare the prepare the logical plan, then optimize it, then the physical plan. That physical plan will be usually MapReduce application. That physical plan will be usually MapReduce application that will read the data from here and do the analytics, get the results, and send it back to the BI tool. Nowadays Hive server, they keep on increasing they keep on updating the Hive server, the community. As a result, they also support a Spark here. Your physical plan will be an RDD code. In case of Spark here, your physical plan will be an RDD code. So that those things, I mean, Hive they keep on updating. It is just a interface on top of the processing framework. That interface will only take care of parsing your SQL queries, preparing logical plans, analyzing, then computing the physical plan. So the physical plan depends on what is the processing engine. So processing engines can be, it's kind of a plug and play. You can just plug in that I want to use MapReduce processing engine or Spark processing engine. Later one more processing framework comes into picture. That support will also be added to the Hive server. So that's how they keep on updating themselves. Or companies, they don't want to use the Hive server, they will directly use Spark SQL as an SQL engine. So they directly use the SQL engine, Spark SQL as the SQL engine, and the Spark SQL will connect the data. So the queries can be given here. The Spark SQL will take care of parsing that query, preparing logical plan, optimized plan, then physical plan. That physical plan will be a RDD code. The physical plan will be nothing but here RDD code. So you will be getting the data from the warehouse, processing it, and displaying it on the web viewer. So these are the places here where Spark fits in. These are the places where Spark fits in. So when I say Spark here, it could be Spark SQL as a library. Here it could be Spark SQL. Both combined together. Spark core language, a Scala based language, or a Spark SQL also could be used here. But but just as a library for ETL processing. Spark SQL will be used as a library for SQL processing. Here it will be as a SQL engine. When it comes in the data analyst part, so it will be like a SQL engine. So this is where our thrift service comes into picture. So it's the same code. The thrift service code is taken from the Hive implementation, and that's how the things work. So I hope the overall bigger picture of where all the Spark fits is clear. Where all the Spark fits is clear. This is our ETL processing. So I assume it is clear. I hope it is clear. So this is the uh, a thrift service. Thrift service. I mean, it's usually used as an abstraction layer for different BI tools. So this is a Java based BI tool. This is a Python based BI tool. This is a Ruby on Rails based BI tool. So all these BI tools, if they want to connect to the Hive server, so thrift service acts as a, one second. Yeah, thrift service acts as a abstraction layer. Any language based BI tools can connect to the Hive server. So that takes care of all the serialization. We will never be writing the code in the thrift service. If at all you are developing your own BI tool, let's say today your company decided to develop a tool, BI tool, using some language. So they wanted to develop a BI tool using Groovy language. This is where you have to learn about the thrift server and how it works, how the serialization is done. Those things will come into picture for BI tool development. So I hope Rohit that was clear. Usually we don't write any code with respect to BI thrift service. Only if you are developing your own business intelligence tool, so then you have to know how these thrift services work, how they serialize your data. Those things we have to understand. So I hope Rohit that was clear. Okay. So these are all the things associated with the Spark SQL. Datasource API, Dataframes, Spark SQL parser and optimizer, Hive Thrift service. We know where the Hive Thrift service fits in. And one more is the Tungsten. Tungsten again. Uh, I haven't worked more into the Tungsten, and usually nobody works in the Tungsten. Tungsten is again a library in our Spark SQL. what does this library does is it does memory management. So if you take a Java program, if you take a Java program, Java, we never write the code to allocate memory. We never allocate the code to delete a memory. Dealloc, malloc, all those things we don't know. We don't do that. We depend on the JVM. Any Java applications, we always depend on the JVM for memory management. We don't worry about those things. Now in Spark, what they have done is they they don't want the JVM to do the memory management, because JVM's memory management in processing huge data in big data space, JVM's memory management is not so optimized. JVM is not suitable. The memory management that we get from the JVM is not so up to the mark when we are using Spark for processing huge data. So that's the reason they implemented Tungsten. So Tungsten does its own memory management. They use some page table kind of a concept, and that's how they implemented the Tungsten. It is all about their own memory management, which is more optimized than the JVM memory management. So that's the idea. So because of this Tungsten, and we also know that the catalyst, we also know that this catalyst, which will optimize your SQL query. Your SQL query will be optimized by the catalyst. Your memory footprint is optimized. Memory footprint is optimized by Tungsten. So because of catalyst and Tungsten, because of this, data frames are faster than RDD. Because of these two components of the Spark SQL library, your data frames are always faster than your RDD. It is just like writing very much optimized RDD code. Probably we may not write the optimized RDD code. So Spark SQL, when we write, it will be converted into an optimized RDD code using Catalyst and Tungsten. Catalyst helps in processing, optimizing the query, which is CPU optimization or processing optimization. Tungsten helps in uh, memory optimization. So Tungsten actually reduces the memory footprint by 50%. It has the capability to reduce the memory footprint. If your in-memory data is about 1 GB, so it can be reduced to 500 MB. So that's what the Tungsten capability is all about. It does its own memory management, which does not depend on the JVMs, because this is much more efficient. As a result, our data frames are always faster than our RT code. So it is always recommended to write data frame code instead of our RDD code. It's always recommended. So I hope till here things were clear. So we'll see some examples now to understand this data source API, to understand the data frames, how things work in Spark SQL. We'll see the examples. So you should see Spark SQL, downloads, training, Spark SQL. Either it should be there or you should see in the left hand panel itself. If you don't see anything in the left hand panel, just click on open, go to the downloads folder, go to the training folder, go to the Spark folder. In the Spark folder, go to the Spark SQL. You can go here. Just press OK. Press OK. You should be able to load the data. Load the project. Sorry. So we'll see the very first example. Here we'll see how to load the data. Loading data using Datasource API. So what do I mean here is, I said that Datasource API is a universal API. This is our Datasource API. So the Datasource API can read CSV file, it can read JSON file, can read XML data, can read ORC, Parquet, Avro, MySQL, Oracle, Postgres. Similarly, it can read NoSQL, NoSQL like Cassandra, HBase, Mongo, and so on. So it can read any structured data or any semi-structured data. So data source API, that's what I said. Data source API is a single universal API for reading any kind of a data, any structured or semi-structured data. So once it reads, it will return a data frame. Just like a comparison, text file API, when we use, it returns an RDD. When we use sequence file API, it returns an RDD. When we use internal API like Hadoop, there are some internal API, Hadoop API, it returns an RDD. Similarly, there is also, just like text file, there is a binary method. It returns a RDD. So binary API is used to read the zip file. So I think just to show that once. Yesterday, I think Saurav had a question. I completely did not show that. I think it was not. Somewhere we will be also, there is a binary also. I think here I'm not using it. So if you are using some internal Hadoop API, these are all the input output operation API. Reading the file, new API Hadoop file. Similarly, Hadoop file is also there. So all these different APIs, text file API, sequence file API, Hadoop API, or new API Hadoop. These methods you use to read the data, they will always give you a RDD. In a similar fashion, we use a data source API to read any of these kinds of data, and it will return a data frame. And it will return a data frame as it's like. So, but it is here we are using only one API. Instead of using different APIs like text file API, sequence file API, we'll be using only one API. Hence, I have said it is a universal API. So that's the reason I have said it as a universal. So first example that we will be seeing is, we will be seeing only how to read the data. We will not see how to process the data. Processing we will see later. Later we will see how to do the processing. So the very first example is CSV file. How to read a CSV file. You can search for, read CSV. This sorry, CSV file dot scala. Search for CSV file dot scala. As usual, we are creating our Spark conf object. As usual, we are creating our Spark context. Now, when we are using our Spark SQL, we have to create a SQL context. Again, as I said earlier, in Spark 2.0, in Spark 2.x, everything is wrapped inside a Spark session. So we have already seen the accumulator example in case of Spark 2.x. So everywhere it was used Spark session. Spark session. Now this is our data source API. Spark SQL on the Spark, once you create the Spark SQL context object, on the Spark SQL context object we have the read here. So this is our data source API. This is our data source API, to which we are specifying the format as CSV, or you can also specify the format in this fashion. Then we say some options we specify, and this is the input path of our file. Load method will take the input path. So which is nothing but our sales.csv. Here, if we are reading the CSV file, we have to specify format as CSV. If you are reading a JSON file, you have to specify the format as JSON. If you are reading an XML file, you have to specify the format as XML. If you are reading Parquet, ORC, Avro, you have to specify the corresponding format. Otherwise, everything remains the same. It's the same SQL context dot read dot format dot load. Read dot format dot load. The same universal API will be used. Now we want our data source API to discover the header. These are the configurations we are actually giving to our data source API. When I say actually the data source API, and I said that the data source API has the ability to discover the schema. This data source API has the ability, so just an API cannot discover the schema. There has to be some piece of code that can discover the schema. Actually, what is there is there are CSV library here, processing I mean the parsing library for JSON. JSON library is there, XML library is there, ORC, Spark, all these libraries are here. So those libraries are nothing but data source libraries. So there are data source libraries. These are all our data source library. This is our data source library. Because just an API cannot do anything. So whenever you read the data CSV or sales.csv file, so the CSV library will be used. That CSV library will parse your CSV records based on the condition. It will determine what is the data type. It will determine what is the column names. All those things will be determined by this library. Similarly, there are libraries for different file formats. But the APIs that is exposed to the developer is only one API. Underneath there will be different libraries which will be abstracting the things and finally giving out a data frame. So that's how the things work. So these some libraries are built-in libraries. Some libraries has to be downloaded explicitly. So these libraries don't come with the Spark bundle. They have to be. It is a third-party library. It has to be downloaded. Here, here CSV is a third-party library. We have to download that library. The data source library has to be downloaded. So how do we know which where from where we have to download? Again, we need to use the Maven repository. So just search for Spark data source CSV. Just search for Spark CSV data source anything. So it will show the GitHub, the code, actual code, and also it will point you to the Maven repository. You can also specify Maven here. So we got our Maven repository. Go there. So as you can see here, this is the Spark CSV library. Latest version is 1.5.0. Copy this dependency, copy this dependency, and paste it in your form.xml. So I am using I have already have that library as specified as a dependency. So if you don't have this dependency, you cannot read a CSV file. So you should add this dependency to your form.xml. It's already there in our Spark SQL project. So once we read, so this option that we are giving it as a map collection. This is how we in Scala we write a map collection. We have seen this hash map collection. So this option that we are giving is the input to our CSV library. We are saying that with this with these things, what we are saying to the library is that while parsing the data, we are saying that the data contains header. The data contains header. You use that header as your column names. That's what we are saying. When we say header is true, we are saying that the data contains header. Use that header and make it as the column names of the data frame. Similarly, we are saying to the data source library, data source CSV data source library, that infer the data type of individual fields. So these are the input configurations that we are specifying it to the data source library through the options. So we are giving options here. Options contains configurations. What all should be done with the data. So here we are saying header equal to true, meaning we are saying to this library that in the data header exists, you determine those header and make them as the column names. And we also said that infer schema is equal to true. When we say infer schema is equal to true, we are saying to the library that while reading the data, you determine the data type of individual fields. That's what the options are used for. Load is to read the input, give the path of the file. So this returns a data frame. As I said, after reading the data, it returns a data. Just like we had RDD earlier, now we have a data frame. Everything we think about data frame is same as RD. Data frames are also immutable. Data frame operations are also lazy. Data frame is also resilient. Data frame it can also be cached. There are actions on data frame. There are lazy transformations on data frames. All those things that hold good for RDD, same things hold good for data frame. So we have some method to print the schema, and we have a method called show. Show is an action here. If we don't have an action, we know that the DAG will not be evaluated. The whole architecture of Spark that we have defined, like there will be a DAG, there will be stages, there will be tasks. So the task will be running in the executor. Everything holds good for the data frame also. Here also you will be having the stages based on shuffling. So here also you will be having actions. So action will evaluate the DAG. So show is a action. So let's run this program. The input that we are giving is our sales.csv. Slightly the sales.csv is changed. Only thing what we have added is we have added a first line as the header here. First line is being added as the header. Hence in the code we are saying that header is equal to true. It says that header exists in the data, and just use it and make it as a column name. So let's run this program and check the output. Okay, I had made some changes. I have to remove those changes, I think. That was a version mismatch error because I was doing some changes. So because of that, this I have to comment. It will take some time to compile because I removed one of the library. It will take some time. So it has exited with code 0, hence it has successfully executed the program. So as you can see here, this is how it will show the data. So it looks just like a table. This is your data frame. So this data frame has a schema. So, sorry for that. Yeah, this data frame has a header. Header is treated as the columns here: transaction ID, customer ID, item ID, and amount paid. And these are the values of that columns. And you can also see I have also printed the schema. So whenever you print the schema, you get to know the data type of individual columns. The data source library, the CSV data source library will will determine the data type. It has determined the data type of integer, of transaction ID as integer, customer ID as integer, item ID as integer, and amount paid as double. So nowhere we have specified. The data source library has that capability. So I hope it was clear that print schema is this, and the table kind of that we saw on the output, it was because of show. And that's the our action. It will just display it. The show method is usually used for display purpose. So if you want to save the data somewhere, we use write dot save. Just like we have read dot load, here we have read, here we have write. Here we have load, here we have save. Write save, read load. So that's how our data source API exists for reading and writing the data. Yeah, here is a question. The question is, if a few rows in the column of a particular, if few rows in a column are string and few integers, what is the data type it will be discovering as? In that case, it will discover as a string. I mean, by default, everything will be string. By default, it will always take the higher data type, which can represent lot of data. So if I say, if I remove this, I don't want to infer the schema. I don't want to infer the schema. In this case, by default, everything will be inferred as a string. So if you see the print schema, everything is inferred as a string. If you specify it as infer schema as true, then it will infer the schema. Similarly, if your data does not have the header, let's say there is no header here. I will delete the header. We did not keep any header. When you don't have the header in your data, then in that case specify header as false. Specify header as false. By default it will be false, so we need not use that at all. So by default header will be always false. So when I run this, so it will generate it knows now that header is not there in the data. It will generate its own headers. So as you can see here, if there is no header inside your data, so then don't specify header equal to true. In that case, it will automatically generate its own header C0, C1, C2, C3. Later you can rename these headers. We'll see those things as well. Now specifying, usually we don't allow the data source API to discover the schema. We don't allow the data source API to discover the schema. How was it able to determine that? It was each column transaction ID was integer, customer ID was integer, item ID was integer, and amount paid was double. How was it able to determine that? How was it able to determine the data type? It cannot magically determine the data type. It has to read the data to determine the data type. No, type inference property is different. Type inference property is different actually. I mean, type inference also is there, but only if you read the data, you can do a type inference. But you have to read the data. Magically, we cannot determine the data type. What I was trying to say here is determining the data type requires the data to be read first. The data to be read first. Only then you can determine the data type. If you take, for example, text file API, if you take, for example, text file API, it does not determine the data type. Nor, or what I am trying to say here is text file API will not read the data unless action is triggered. Only when action is triggered, you will read the data using the text file API. That does not hold good for the data source API. We can say that data source API is not lazy. Data source API is not lazy. It will read the data just for inferring the schema. And again when the action is called, once again it will read the data from the disk. So if you are trying to infer the schema, the data source API will read the data. It will infer the schema. And when the action is called, again it will read the data and do the processing. So data source API is not lazy, and inferring schema makes the data to be read twice. When we say infer schema equal to true, the data is read twice. Once for determining the data type of individual columns. To determine, it has to read the data, and once when the action is called. So if your data is 10 GB, actually you will be reading the data two times, so 20 GB. So it is usually you don't specify infer schema equal to true. I mean, in most of the cases where you already know the data type, if you already know the data type, you can explicitly specify the schema. That's the reason these are the points I have set it. The data source API has the ability to accept the schema, which is explicitly specified. A developer can explicitly specify schema, so that specified schema, the data source API can accept it. So in this case, the schema discovery will not happen, in which case the data will be read only once during the action. So it has ability of discovering schema has its penalty. It has to pay the penalty of reading the data twice. So if to avoid that, you can explicitly specify the schema, and in most of the cases you will be specifying the schema. In most of the cases where you already know the schema. If you don't know the schema, then we don't have any other option. We have to we have to discover the schema. So I hope those things were clear here. I hope these things were clear. Datasource API is not lazy when you say infer schema equal to true, because inferring the schema requires the data to be read. As a result, the data will be read twice, once to infer schema, once when the action is called. So to avoid that, we can explicitly specify the schema. So we can specify the schema using, there is a method called schema. So it takes a struct type, so you have to specify a struct type. We will see how to specify that as well. We'll also see how to specify that. In which case the data will be read only once when we call the action. Yeah, so let's wind up the session here, and let's continue tomorrow. Tomorrow we'll see how to read a JSON file, how to read an XML file, and how to process the data, how to specify schema. Those things also we will see. So thanks everybody. Have a nice day, and good night others.